Now we move on from the basic rectifier configurations into the basic DC power supply. How do we use the rectifiers and the filters that we learned about to come up with an efficient and effective DC power supply? The DC power supply converts the standard 120 volts, 60 hertz AC available at wall outlets into a constant DC voltage. It's one of the most common electronic circuits that you will find. You use it to charge your phone. The DC voltage produced by a power supply is used to power all types of electronic circuits, such as television receivers, stereo systems, VCRs, computers, and lab equipment. As you know, a rectifier can be either a half wave or a full wave rectifier. The rectifier converts the AC voltage, input voltage, into a pulsating DC voltage, which is half wave rectified, as shown in the diagrams below, or full wave rectified. A block diagram for a power supply is shown in part C. So if we look below here, we can see we've learned about the half wave rectifier, how we only get half of the signal out. We've learned about the full wave and the full wave bridge rectifier, where we actually get the full rectified output. So now what we're going to do is try to learn something, figure out how do I take that rectifier output and filter it and turn it into a smooth DC signal or power. So when we connected to the rectifier, a capacitor filter eliminates the fluctuations in the rectified voltage and produces a relatively smooth DC output. The regulator is a circuit that maintains a constant DC voltage for variations in the input line voltage or in the load. Regulators vary from a single device to more complex integrated circuits. The load block is usually a circuit for which the power supply is producing the DC voltage and the load current. I'll say at this point, if power supplies intrigue you, there's a course that is an advanced power supply course that you can take later on in your educational career here that offers some of the most up-to-date types of theory and design on power supplies. So now we take a look at what the capacitor input filter will do when added to a rectifier circuit. A half-wave rectifier with the capacitor input filter is shown below in A. The half-wave rectifier is used to illustrate the filtering principle. Then the concept will be expanded to the full-wave rectifier. So in looking at this, during the positive first quarter cycle of the input, the diode is forward biased. Okay, we got to get past that bias voltage if it's a silicon of 0.7 of a volt, allowing the capacitor to charge to approximately the diode drop of the input peak. Okay, and we can see that in A, where we've got our input, and we can see what's going on in the output here over the filter. When the input begins to decrease below its peak, as shown in part B, the capacitor now is retaining its charge and holding that level to a higher level instead of just letting it drop off. The diode then becomes reverse biased during the remaining part of the cycle. So we can see here what's going on. The diode is charged, it's holding the signal, and although it is starting to decay, it's at a much slower rate than you would normally see. So the capacitor discharges through the load resistor after the peak of the positive alternation when the diode is reverse biased. This discharging occurs during the portion of the input voltage indicated by the solid dark blue curve. So in part C, the capacitor charges back to the peak of the input when the diode becomes forward biased. This charging occurs during the portion of the output voltage indicated by the solid dark blue curve. So we see that during that cycle then, the capacitor can discharge only through the load resistance at a rate determined by, guess what? The RC time constant. The larger the time constant, the less the capacitor will charge. Because the capacitor charges to peak at a value equal to, remember V peak in, the peak inverse voltage of the diode in this application then, and we've seen this before, peak inverse voltage is equal to 2 times V peak in. During the first quarter of the next cycle then, illustrated in C, and we can go back up and look at that. So there's C. You can see what's happening here. We get to the point in the input wave where it starts to increase. The capacitor is charging then, and it repeats what we saw in the first part. So during that first quarter, the diode again will become forward biased when the input voltage exceeds the capacitor voltage. So what we're looking at here then becomes something called ripple voltage. As you've seen, the capacitor quickly charges at the beginning of the cycle and slowly discharges after the positive peak when the diode is now reverse biased. The variation in the output voltage due to the charging and discharging is called the ripple voltage. The smaller the ripple, the better the filtering action. Okay, so we can see here what's going on here. Here we've got a fairly large ripple. Here we've got a smaller ripple. So this is your half wave and the ripple that occurs. For a given input frequency, the output frequency of a full wave rectifier is twice that of the half wave rectifier. As a result, a full wave rectifier is easier to filter. When filtered, the full wave rectified voltage has a smaller ripple than does the half wave rectifier. The smaller ripple occurs because of the capacitor discharging less during the shorter interval between the voltage pulses. A good rule of thumb for effective filtering is to make the RC time constant much greater or equal to a period of 10, okay, where T is the period, so 10 times the period. So we can see here what the difference looks like between a half wave and a full wave rectifier. The ripple factor, R, is an indication of the effectiveness of the filter and is defined as the ratio of the ripple voltage, V sub R, to the DC average value of the filter input voltage, VDC. These parameters then are illustrated in the next diagram. So the relationship, the ripple factor, is equal to the ripple voltage divided by the average DC value times 100%. So we can see here, in this case we've got VR versus VDC. The lower the ripple factor, the better the filter. The ripple factor then can be decreased by increasing the value of the filter capacitor. Now we take a look at, I'm just going to kind of go over this here, integrated circuits for regulated power supplies. While filters can reduce the ripple from power supplies to a low value, the most effective filter is a combination of capacitor input filter used with an integrated circuit, okay, as a voltage regulator. The most popular IC regulators have 3 terminals: an input terminal, an output terminal, and a reference or adjustable terminal. 3 terminal regulators designed for fixed output voltage require only external capacitors to complete the regulation portion of the power supply. They give you an example of a 3-terminal 78XX series positive regulator, and you can see here they've strapped one onto a bridge full wave rectifier here, And so this is going to give you a cleaner 5-volt output. So take a look at that to gain a better understanding. Another type of 3-terminal regulator is the adjustable regulator. One of the most popular is the LM117/LM317 series adjustable positive regulators. Okay, if we take a look at this, we've got a relationship here that tells us the output then can be calculated as 1¼ volts times R1 plus R2 divided by R1. And so in the circuit here we can see that basic power supply with a variable output voltage from 1¼ to 6½ volts. Okay, so this starts getting fairly complex. Later on in your education, you'll learn more about this and possibly building these in the lab. Percent regulation. The regulation expressed as a percentage is a feature of merit used to specify the performance of a voltage regulator. It can be in terms of input line regulation or load regulation. So the relationship here says line regulation then is equal to delta V out over delta V in. That's just the change in the voltages times 100%. Load regulation specifies how much change occurs in the output voltage over a certain range of load current values, usually from a minimum current no load to a maximum current full load. So you can see we take the difference in the no load versus the full load and divide it by the full load times 100%. If we take a look at this example, assume a certain 7805 regulator has a measured no load output voltage of 5.18 volts and a full load output of 5.15 volts. What's the load regulation expressed as a percentage? So you can see we're going to use the load regulation formula, no load minus full load divided by full load times 100%, and we get a little over 50%, almost 60% as the load regulation.